Welcome back to this next video in which we are discussing direct sums of subspaces. Okay, right, so in the previous video what we did is we defined the sum of a bunch of subspaces, and we saw how the sum of a collection of subspaces is always another subspace of our larger vector space which we're doing everything within. Okay, so what we're now going to do is we're going to have a look at the definition of what is meant by independent subspaces, and that will then allow us to turn sum of subspaces into a direct sum of subspaces, and we'll finally see what a direct sum of a bunch of subspaces is. Okay, so let's now see what is meant by independent subspaces then. Okay, so the definition of independent subspaces then is very much so tied in with the definition of the sum of a bunch of subspaces. Okay, so let me write this out. So first I'll just underline independent subspaces in turquoise here, and now what I'll do is once again we have a bunch of subspaces, capital W1, capital W2, all the way up to capital Wn, and these are all subspaces of the vector space capital V. Okay, so what is meant by these being independent? Okay, well this means that if you consider what the sum of these n subspaces is, so if you consider capital W1 plus capital W2 plus all the way up to capital Wn, of course this will be the set that contains all things of the form little w1 plus little w2 plus all the way up to little wn, where these little wi's are elements of the capital Wi's. Okay, so you take all combinations of elements from these n subspaces of capital V and you add them together. Okay, now if they're going to be independent, what it means is that there is only one way of adding together n vectors from these n subspaces and getting the zero vector as your answer. Okay, so if we consider little w1 plus little w2 plus all the way up to little wn, and we want this to equal the zero vector, there is only one solution to that. Okay, so if you want to add together n vectors, one from each of these n subspaces of the vector space capital V, and get the zero vector, there's only one solution to that, and that has to be the trivial solution. Okay, so we saw that the zero vector is always an element of the sum of a bunch of subspaces, and the reason is that because these are all subspaces, the zero vector will be an element of all n of them. Okay, so one of these sums that you can construct here of elements from these subspaces is where you pick the zero vector for all of these. So you let little w1 equal the zero vector, little w2 equal the zero vector, and so on, all the way up to little wn, and you let that equal the zero vector, and you add together n lots of the zero vector, and of course that will also give you the zero vector as your overall answer. Okay, so that's called the trivial way of getting the zero vector, the trivial sum that you can have which will give you the zero vector. If these subspaces, capital W1, capital W2, all the way up to capital Wn, are going to be independent subspaces, that has to be the only way. Okay, so there cannot be a non-trivial combination of vectors from these n subspaces which gives you the zero vector. Okay, so if you go through absolutely every single possible combination of elements of these subspaces and you add them together, okay, so you take every possible combination you can and you go through all of them, the only one that will give you the zero vector will be where all of these vectors that you've picked from the subspaces are the zero vector. Okay, there will be no other ones which give you the zero vector. None of the non-trivial combinations will give you the zero vector, only the trivial combination, if they're independent. Okay, so that's the definition of a bunch of subspaces being independent. It means the only combination, the only sum of elements from these subspaces which gives you the zero vector is the trivial one. Okay, now this then means the instant this is true, it means that something else is going to be true. Okay, and the new thing that's going to be true is that actually all of these distinct sums that you can construct, where you're using a distinct combination of elements from the subspaces capital W1, capital W2, all the way up to capital Wn, all of these sums will be distinct elements in the vector space. Okay, what I mean by that is that if we have a vector in the vector space which is in this sum of the subspaces capital W1, capital W2, all the way up to capital Wn. So let's say little v here is an element of capital W1 plus capital W2 plus all the way up to capital Wn. Okay, there will only be one combination, one sum of elements from the subspaces which actually gives that vector v if the subspaces are independent, which means that the only sum of elements from the subspaces which gives the zero vector is this trivial sum. Okay, so I want to prove that now. Okay, so the way that I'm going to prove that is by proof by contradiction. So I'm going to assume that we have this little v, which is an element of the sum of the subspaces capital W1, capital W2, all the way up to capital Wn. And what I'm now going to do is assume the exact opposite of what I want to prove. I'm going to assume that there are two different sums of elements of the n subspaces, which will give me this same vector. Okay, so I'm going to assume that I can write little v as being little w1 plus little w2 plus all the way up to little wn. So there is one sum of elements of the subspaces which will give me this vector v. But let's say that there is another sum, a different sum. Okay, so we'll have little w1 bar plus little w2 bar plus all the way along to little wn bar. Like so. So there is our second sum of elements of the subspaces capital W1, capital W2, all the way up to capital Wn, which gives me this vector little v. Okay, so I've assumed the exact opposite of what I want to prove, and now what I want to prove is that this proves, I can use this to prove that these subspaces capital W1, capital W2, all the way up to capital Wn are not independent, i.e. they do not obey this criterion. So I'm going to prove that I can find a non-trivial sum which gives me the zero vector. Okay, so what I just want to stress here is that these vectors that I've got from the subspaces, they're not necessarily all different from the vectors up here. It's just that some of them have to be different. So what I mean by that is potentially W1 here and W1 bar could be the same vector. Okay, it's just that the entire sum has to be different. Okay, so at least one of these has to be different. So potentially W2 and W2 bar, maybe those are the different ones. Okay, so something in this combination of elements from the subspaces has to be different between these two, but it doesn't necessarily mean that each one that you've picked from the different subspaces is absolutely different all the time. Okay, some of them might match up, it's just that we have to have at least one that doesn't match up, basically. Okay, right, so I'm going to use this fact that I have these two different combinations of elements from the subspaces which sum to give this same vector in the vector space to then find you a non-trivial sum which gives you the zero vector. Okay, so quite simply set these two equal to each other, and what we get is the equation that W1 plus W2 plus all the way along to Wn is equal to W1 bar plus W2 bar plus all the way along to Wn bar, like so. Okay, so that's perfectly valid to do if this sum is overall equal to this vector and this sum is equal to the same vector, then I can set the two sums equal to each other and they certainly will equal one another. Okay, what I can now do then is add onto both sides of this equation the additive inverse of these vectors W1 bar, W2 bar, all the way along to Wn bar. Okay, so I'm going to add onto both sides the additive inverses of all of the things on this side. Okay, then what I'm going to do is apply associativity and commutativity of addition to say that I can put these additive inverses wherever I like on this left-hand side. So what I'm overall going to get then is W1 plus the additive inverse of W1 bar, okay, plus W2 plus the additive inverse of W2 bar, plus all the way along to Wn plus the additive inverse of Wn bar, and then we'll end up with the 0 vector on this side because all of the additive inverses would have cancelled with these vectors, and we'll end up just with the 0 vector there. Okay, so here now, this statement is going to be perfectly true if the red statement is true. So I've just turned the red statement into this statement here. Now, let me put some brackets into this expression. So because addition obeys associativity, I can put brackets wherever I like. So I'm going to put one bracket around these two, I'm going to put another bracket around those two, and so on. I'll put a bracket also around Wn plus the additive inverse of Wn bar. Okay, now, I remember said that not all of these pairs matched up. They're not necessarily all different, but at least one of these pairs does not match up. Okay, so let's say, for instance, W2 and W2 bar did not match up. They were different. Okay, there must exist one pair, at least one pair, where they do not match up. Okay, then what we will end up with here is W2 plus the additive inverse of W2 bar. That will not equal the 0 vector, okay, because this is not going to be the additive inverse of W2. Okay, and I've missed out a step in. I've missed out an explanatory step here. So let me just take a step back and go back to what I need to say before I go on to that. Okay, so the important thing, why have I put the brackets around these things like so? The reason I've put the brackets around these is because W1 and W1 bar are both elements of the subspace capital W1. Okay, so that means that the additive inverse of W1 bar here will also be an element of capital W1. So I'm adding two elements of capital W1 here together, which of course will give me another element of capital W1. This argument extends on. Okay, so here we've got W2 plus the additive inverse of W2 bar. Of course, that will be an element of capital W2. Okay, and we continue on all the way down here where we've got Wn plus the additive inverse of Wn bar, and of course that will be an element of capital Wn. So here we have something of the form an element of capital W1 plus an element of capital W2 plus all the way up until we've got an element of capital Wn. Okay, so, and the important thing is here that it's adding together to give the 0 vector. Okay, so if these were independent, then the only possible combination here would be a 0 vector here, 0 vector here, all the way up to a 0 vector here. You'd have to have a 0 vector in all of these positions. Okay, but I claim that we have not got a 0 vector in all of these positions, because if these two were distinct sums here, they were distinct combinations of elements from the subspaces capital W1, capital W2, all the way up to capital Wn, then at least one of these pairs doesn't actually match up. Okay, and we said W2 was not going to be the same as W2 bar, for instance. That means that this element of capital W2 here would not be the 0 vector. Okay, so at least one of these things in this sum now would not be the 0 vector, and therefore we'd have a non-trivial combination, a non-trivial sum, which was giving the 0 vector, and that would contradict these subspaces being independent. Okay, so the instant that you know that these subspaces are independent, i.e. that there's only one combination of elements from the subspaces that you can take and add together to get the 0 vector, then you instantly know that all of the different combinations that you've got here of elements from the different subspaces added together will be different elements in the vector space. They are all distinct. No two different combinations are going to sum together to give the same vector in the vector space. Okay, so there's no degeneracy here, and that's why the concept of independent subspaces is going to be so important. Okay, why it's going to merge with this concept of summing vector spaces to give the concept of the direct sum of a bunch of vector spaces. Okay, but before we go on to the concept of a direct sum, what I just want to do is give you a little bit more intuition with regards to independence of a bunch of vector spaces, or rather a bunch of subspaces, by showing you what it means for just two subspaces of a vector space to be independent. Okay, so let's say we have two subspaces of a vector space. Let's say we have capital W1 here and capital W2, which are subspaces of our vector space capital V. I claim that W1 and W2 being independent, okay, and I'll just abbreviate independent down to I, so W1 and W2 being independent is utterly equivalent to, is equivalent to saying that the intersection is equivalent to saying that the intersection of these two, so W1 intersect W2, is equal to the zero vector. Okay, so basically these two subspaces, W1 and W2, which are subspaces of our vector space capital V, will be independent if and only if the intersection of the two of them is equal to the zero vector. So the only vector that's in both of them needs to be the zero vector. Okay, so I now want to prove this. So we need to prove it in two directions. So one direction that I want to prove is that if they're independent, then their intersection is equal to the zero vector. But the other way around I want to prove, and I'll prove the other way around first, is that if their intersection is the zero vector, then they are independent. Okay, so let's start with that one. So we'll have these two subsets, W1 and W2, and we're going to start off with their intersection being the set that contains just the zero vector. So the only thing that both of them contain is the zero vector. Okay, what I now want to prove from that is that they are independent subspaces. Okay, so to prove they're independent, I want to prove that there is no way that you can add one vector from capital W1 to a vector from capital W2 to get the zero vector except the trivial way, which is this is the zero vector and this is the zero vector. Okay, so if we've got a non-trivial combination, okay, well, firstly, the way I'm going to do this then is proof by contradiction. So I'm going to assume the exact opposite of what I want to prove. Okay, so I'm going to assume they're not independent, which means that there will be a non-trivial combination of an element from capital W1 with an element from capital W2, such that when I sum them together, it gives the zero vector. And I'm going to use that to disprove the fact that their intersection is just the zero vector. Okay, so let's do this then. So if I've got a non-trivial combination here, W1 plus W2, which gives the zero vector, okay, the first thing that I need to say is that it cannot be the case that one of these is the zero vector and then just the other one is not the zero vector. Because if one was the zero vector and the other wasn't the zero vector, then how could you add 0 to a non-zero element and get 0 back again? You'd get the other element back again. Okay, so what that has to mean is that both of these have to be non-zero elements. So W1 and W2 are non-zero elements. Okay, so I can therefore say that W1, let's say here, is not equal to the zero vector. Okay, therefore, just looking at this statement, what does that mean about W2? It means that W2 is the additive inverse of W1. Okay, just by definition, because W1 is adding to W2 to give the zero vector, so therefore W2 is the additive inverse of W1. And what that means is that the subset, the subspace capital W2, contains the element, the additive inverse of W1. Okay, so because W2, little w2, came from the subspace capital W2, it means that the additive inverse of W1 must be an element of capital W2. But because subspaces are closed under addition, that must mean that this subspace capital W2 also contains capital W1. Okay, so this instantly implies that capital W2 also contains capital W1, because if it's a subspace, it has to contain the additive inverse of any element that's in it. Okay, so the additive inverse of the additive inverse of W1 is W1 itself. So we now have the statement that W1 is an element of capital W2, but we also know that little w1 was an element of capital W1 because it was the element that we had picked from capital W1. Okay, so what I've now proven is that both of these subspaces contain this element, little w1, which was not equal to the 0 vector, and therefore that contradicts the intersection of these two subspaces being the set that contains just the 0 vector. Okay, because now I've found another element that's not the 0 vector that's in both of them. Okay, so what I've now proven then is that if the intersection of two subspaces is equal to just the set containing the zero vector, the zero subspace here, then those two subspaces will be independent. Now what I want to do is go the other way to prove that they're truly equivalent statements. So I want to prove that if we have it the case that these two subspaces are independent, then I can prove that the intersection of them is equal to the zero vector, or is equal to the set that contains just the zero vector. Let's get a new piece of paper here and do this. Okay, so we start off then with the statement that these two subspaces are independent. Now what that means is that the only solution to this equation, w1 plus w2 is equal to 0, is equal to the solution where both of these are the zero vector. Okay, that is the only solution. That's the definition of these two subspaces, capital W1 and capital W2, being independent. What I'm trying to get to is the fact that the intersection of W1 with W2 is equal to the set that contains just the zero vector. Okay, so the way I'm going to prove this is by, again, a proof by contradiction. Okay, so I'm going to assume the opposite of what I want to prove is true. Okay, so I'm going to assume that the intersection of these two subspaces, capital W1 and capital W2, is not just the set that contains only the zero vector. Okay, so instead, let's say that there is some other vector which we'll call little v, which is an element of capital W1 intersect capital W2, where v is not the zero vector. Okay, so I'm saying that the intersection contains more than just the zero vector. Okay, what I'm now going to do is use this to disprove this statement here. I'm going to disprove that W1 and W2 were independent. So the way that I can do this is by saying, okay, if little v is in the intersection of capital W1 with capital W2, then that means that little v is an element of capital W1 and little v is an element of capital W2. But both of these are subspaces, which means that they have to contain the additive inverses of all the elements that they contain. So this means that the additive inverse of v is also an element of capital W1, and the additive inverse of v is also an element of capital W2. Okay? So what I can do then is I can easily find you a non-trivial combination of elements from the subspaces capital W1 and capital W2 that you can add together to give the zero vector. Just let little w1 here equal v, and let little w2 equal negative v, the additive inverse of v, and of course when I add these two things together I will get the zero vector, okay, because just by definition, and therefore I have a non-trivial combination of elements from these subspaces capital W1 and capital W2 which will sum together to give the zero vector, disproving therefore that capital W1 and capital W2 are independent. Okay, so the instant they are independent, their intersection has to be just this set that contains the zero vector. So indeed those two statements that W1 and W2 are independent and W1 intersect W2 is equal to the set that just contains the zero vector are utterly equivalent. Okay, so we'll call it there for this video, and in the next video what we'll do is introduce the definition of a direct sum.